You've seen the contents of the course on the website. Very quickly, you will see a mix of practical aspects of parallel programming and development of theory of parallel algorithms, models of parallel computation. So, you will get some theoretical background as well as learn to practice parallel programming on modern parallel computers. Let us begin with some motivation. This is what is now famously known as the Moore's law, a statement by Moore in 1965, which predicted that over the next 10 years computers will become fast, very fast. When those 10 years elapsed, it turned out that the computers continued to become fast, very fast, and it's basically been revised to saying that the computer speed is going to be essentially doubling every 18 months. And that happened by a variety of techniques. In the beginning, that estimate of 24 months, 12 months to which was the 1965 statement to double the speed was based on the fact that there is a lot of innovation in science and engineering to be done to make computers go faster. And in 1975, Moore predicted that we have essentially saturated our intelligence. We cannot make innovations into making things better and faster, but still just by the advent of technology of being able to lay thinner wires on the silicon, we will be able to pack in more and more and more transistors, which will in turn make computers faster. Okay. And so, there are two parts to it. One was that you can drive the clocks much faster, drive the gates using a faster clock, which as you probably have seen has saturated in the last few years. You do not see the 90s style going from 1 gigahertz to 1.5 gigahertz to 2 gigahertz computers coming on, but still new computers keep coming on, and it is because the law still holds. Even today, you are able to, law does not really say anything about fast, it says about you can pack more circuitry in the same amount of space, okay. And that has continued to hold. The challenge is to make that circuitry do things that you want to do, okay. And part of the speed up happened because of the increasing clock cycles, increasing clock cycle speeds, but part of it is happening because we have much more compute engines on the chip that can do many things at the same time, okay. So, that is one reason that parallel programming has kind of started to become popular. There used to be a niche area for a long time. There even used to be, we will go through the history a little bit. There used to be massively parallel computers which were practically less of a compute engine than PCs of today, being sold for millions of dollars at the time. But that kind of work died down around 90s, and then with the advent of Intel's PC based or rather Intel based chips for microprocessors, led into a slightly different direction than the earlier direction, and now Intel itself is trying to pack more and more and more cores into a single chip, so that you can do more at the same time. But only being able to pack more cores does not always help. You have to be able to use those cores to actually do things at the same time that together mean something, okay. Having clocks running at 24 cores or 100 cores or 1000 cores does not give you any computation. At the end of the day, each clock you have to do some work that can be, whose result can be used later on by somebody else, right. So, that is essentially what we need to study. So, in short, clocks stopped getting faster, but you can in fact pack more and more information, more and more circuitry, more and more data parallel paths on a single chips. Chips are getting bigger in terms of how many gates they have, not in terms necessarily, although they are getting bigger in size also somewhat, especially NVIDIA keeps increasing the size of its chips, but it is more of the packing density on the chips that is going up, which is causing many more compute engines to be available at the same time, which we hopefully would be able to use in a useful way if we were able to do parallel programming efficiently. And even if we have all these processors, you can make the processors go faster and faster. You can say this processor is 10 core processor, is a 20 core processor, which can somehow internally figure out how to parallelize your application. So when you have a program that is a list of instructions, it takes the next 100 instructions and executes in parallel. Right? There have been architectures where you essentially compute without too much analysis of what instruction needs to happen before what other instruction. You just predictively run many instructions, and some of those instructions will not have their data because they depend on previous instructions that haven't happened yet. And you throw away the results of those instructions. You just use the results of instructions that had their data at the time they were run. And so that is in some sense brute force parallelism. Okay. It can take you only so far. But even if you were able to make the processors faster and faster and faster, that is not going to be the end of the story, because ultimately you need data on which the processors will be doing something. You need operands on which the operations will happen. Okay. And these operands will stay in the memory, DRAM, or probably come from network through some I/O interface, and those are not going up in speed nearly as fast as the processors. Okay. So while processors speed, although in again using it in layman's terms, is going up by doubling every 18 months, that DRAM speed is basically going up by 10% every year or so. Okay. So the lag is only going in higher and higher and higher. All right. Making good use of parallel architectures and parallel programs also helps you with that disconnect, because now, because a single DRAM chip cannot be accessed fast enough with a processor that is running really fast, but if you have hundreds of processors connected to hundreds of DRAM chips, each can probably be matched with the speed of the DRAM. Okay, because each processor is slightly slower than the number of operations per second that you can run. All right. So that is another reason why parallel programming has started to grow, because the architecture simply cannot have a single CPU connected to a single memory bus with a single memory hanging on the other side. Okay. It just does not scale. The memory becomes the bottleneck too quickly. And in fact, the Googles and the Yahoos of the world are focusing on that side of the story. How do you pump operands into the CPU fast enough so that the operation can be done? And so some of the research has shifted into that interface between the CPU and the rest of the architecture. Okay. Let me also very quickly go through some sample applications. You might consider using these as kind of test beds or target applications for your projects at the end of the course. These are some of the areas, not all, some of the areas where high speed parallel computation has become very popular because of the need for it, because the amount of computation that is needed is extremely high, and they were always being done on supercomputers, and supercomputers were in some sense on the leading edge of being able to parallel program. But now that technology has become available to everybody, that kind of skill is required in a much more wider context. Okay. And so here are some examples of how fast these applications would run This is probably 2 to 3 year old data at this time. So, n body simulation with a million bodies, and again it depends on the simulation. So, do not take the exact numbers without any grain of salt, because there is lot of information that is not being provided to you. It is just at a high level. One example of n body simulation that runs at days per iteration. Okay. Atmospheric simulation, weather simulation is an extremely, let us say, hot topic recently because of global warming. Simulation of how atmosphere will behave 50 years from now, 100 years from now, is what people are doing on computers. Okay. And being so, you have probably seen how well we can predict tomorrow's temperature. So, that is because our models are still evolving, and we have to predict tomorrow's temperature today. We cannot wait until day after tomorrow for the model to complete its computation and then say yesterday's temperature was 7 degrees. Okay. And so, there is a lot of computation being thrown there, but still there is lot more to be done. The entire area of weather simulation, atmospheric simulation has seen massive application of large number of supercomputers or multi-core machines. People are using it in movie making all the time. Computer graphics at a very high quality, does not come cheap, and that happens to be a problem that is easily parallelizable. Right? The generation of a movie essentially is generation of many images in a sequence, and you can generate an image of 2 minutes later in the movie at the same time as you are generating the image of now. And so, that is what is sometimes called embarrassing parallel, because there is, you just, as many computers as you have, you can use them all without worrying about what comes before, what comes after, whose result needs to go to whom. All that information or headache is not there in that problem. But still, movie making on a cluster of machines still takes somewhere from a few minutes, depending on how complex the scene is, to a month of time per minute for highly complex scenes of animation movies. Okay. Oil exploration is another area where, because the payoff is so high, people want to get there first. People want to make the computations about fitting of model in terms of where that oil may be found in the vast expanse of ocean or earth, is another place where people are seeing a lot of explosion of parallel programming. Stock pricing, again high payoff potentially, lot of data centers on the Wall Street, and a lot of people from here using those data centers. Again, computational biology, bioinformatics in general has a lot of simulation of genes, sequencing of genes, how genes would evolve and things of that sort. Again, lot of computation is needed, and naturally people are moving towards using at least moderate sized, if not massive sized data centers for those cases. Here is one picture of one row of, or rather 2 row of racks in a data center of some unknown named company. This is not Google's data center, which this information is coming from somewhere else. Google's data center, so one of Google's data center is 68,000 square foot, another one is 140,000 square foot, and each of these things going vertically is a single rack, and then there is a sequence of racks that is in this photograph, and there is probably something close to 40 or 50 racks in a row. Each rack, depending on the age or when it was built, is going to have 40 to somewhere close to 80 CPU boxes, CPU/GPU boxes, some server. And so, just imagine so much of space filled volumetric area and height with processing that needs to be controlled, needs to do something useful. Of course, typical uses of these data centers are in that context of embarrassingly parallel, because there are lots of users trying to do different things, and so there are technologies like virtualization, which takes this data center, breaks it up into logical machines that each user is basically using on his own or her own, and so they are not really being massively parallelized. One single application is not run on the entire data center typically.
Is this parallelization of computation or storage?
Computation as well as storage. Typically, for example, a Google data center will have with each node enough number of CPU boards and enough number of disks. It is a data center.
Typically, these are like normal machines. Normally, data centers they have machines which are optimized in a way that more and more machines can be put in a single rack.
These are, and in fact, it's less of an optimization of space as much of the interconnect and the power, which is where Google makes its own.
Air conditioning requirements means more power.
No, but the fact is that they are still buying these 1U boxes from the market and putting it there, right. So, that 1U box is going to take its space, you can do nothing about it. In this case, it is not 1U boxes, but a typical data or an example of a data center would be just buying 1U boxes and putting them up in a rack, all right. And in fact, that number is coming from 40 to 80 servers is because there are these two-sided racks which can hold 20 1U boxes on one side and 20 1U boxes on the other side. Recently, Tianhe-1, which was listed as the fastest supercomputer in the world, which is made of 14,000 Intel Xeon processors and some 7,000 NVIDIA Tesla GPUs working together. In this case, it is not like a data center where there are lots of independent processes, independent programs running. Single program being speeded up by using all of these different CPUs and GPUs at the same time, okay, which is more in line with what we are going to be talking about in this course. All right. Let us move on to thinking about. So, this is just a very brief update, so to speak, on those of you who have done and even those of you who have not done OS and intro to computers type stuff. We execute stored programs on computers of today typically, and in a sequential context, you have got a list of instructions one after the other, and there is an CPU execution engine which is going to read the operation opcode and the operands and perform that, okay. And there is some fetch and execute cycle, but typically it is going to go one after the other, right. One instruction executed, then the next is executed and the next executed, and of course, there is some notion of jumping and looping and all that, right. You can go forward, you can go backward, but typically one instruction at a time. Whereas, in the parallel context, you have independent streams of these instructions, and that is really the basic difference. Independent streams being executed independently, right, at the same time. So, two different PCs, program counters being incremented at the same time. Okay. There is no saying where this program counter is with respect to that program counter, right. This might have been incremented 5 times, that might have been incremented 10 times. We are not going to make any assumptions about how synchronized they are or unsynchronized they are. Okay. So, each one is going to do whatever it does in a sequential context, but it happens at the same time. Strictly speaking, this is, although I am saying that is parallel, this is sequential, even in sequential machines you have this notion of non-determinism, right, because even though at the processor level there is a sequence of instructions and it executes one after the other, at the application level there are many different processes, many different threads and context switches among them. Okay. And if these threads or processes have any knowledge of each other, right, if they communicate with each other, then it boils down to the same thing, right, because there are two independent threads. You do not know how many instructions of this thread has run, how many instructions of that thread has run, and you still need to somehow be able to manage them, figure out what data that this thread produces can be used, consumed by that other thread. Okay. So, although slide on the right hand side said parallel, strictly it is concurrent. Okay. All right. And in terms of communication, there are two styles of communication, so to speak, that are followed. In the older days, there used to be, you have a shared memory computer or you have a message passing computer. These days, you have a shared memory and a message passing computer. Okay. Most practical machines on which you will do parallel programming will have some notion of shared memory as well as some notion of communicating with some other processor. Okay. Shared memory is also one way of communication. You put some data in the shared memory, the other processor reads it from there. So, you have communicated that data. But shared memory means a shared address space. So, when you say I am writing this data to variable number, variable named alpha, and the other thread needs a value of alpha, it can figure out the address of alpha, go to that address and read it, right. So, there has to be some notion of shared address space also. In message passing, you basically have some network. I have got a packet of data, there is no address on it. There is an address on the receiver, and I say this data needs to go to that receiver. And the receiver, if the receiver is willing to accept that data from the sender, then some protocol needs to be followed, some handshake needs to be followed, and that data will get from the sender to the receiver, and the communication has happened. Okay. OpenMP is going to be basically on the left side, right. OpenMP is using the shared memory model only, and MPI, which is short for message passing interface, is going to be on the right hand side. Okay. And you can use OpenMP as well as MPI in the same program, probably because two of the cores that need to interact do not have a shared memory, or even if they have a shared memory, for some reason you decide not to use the shared memory, not to share an address space, and you send the data by using some protocol. And we are not going to get, again, as I had mentioned earlier, into the types of protocols, the types of issues with sending data. Just going to assume it, we are going to say all of that is inbuilt in something like an MPI or OpenMPI toolkit. We are just going to assume it is there, we are going to use it. Okay. Sometimes we will care about how far something is, because getting data to a far away place takes more time, but usually we will simply say this data needs to go one hop to somebody else, and so it takes 1 unit of time. Okay. Continuing on a little bit more about the concurrent stuff. So, what happens if this program runs in a sequential context? I want to withdraw something from the ATM. I say this is the account number, this is the amount of money to withdraw. You say current balance is equal to query a database. I get the balance of that account number, and if the current balance is greater than that amount, we set the balance to the old balance minus whatever we are withdrawing, and then eject that money from the ATM machine. Okay. So, this is proper program if there is only one user, one database. But what needs to happen when you have many ATMs all connected to some notion of a logical database which may or may not be at the same place? What will happen if this program runs? Race conditions, right. So, we have two ATMs, right, and you go and query on the both ATMs for the same account number, because you can get multiple ATM cards for the same account. and you say current balance is equal to 1000 rupees, right, and you say okay, I can withdraw 500. Both of them check that current balance, which is 1000, is greater than the amount I am withdrawing, which is 500. So, they set the balance to 1000 minus 500. So, the amount in the database says 500, and then you eject 500. So, what happened? You ejected 500 twice, but the database got updated by the it got updated twice in this case, by the same value, right. Both of them said update it to 500. And so, kinds of things that you need to moderate are, and what was shared here? The current balance, right. When you did the query to the database, we are querying about the same account number. Okay. So, there is that notion of shared, and so whenever you have got multiple players trying to share a resource, you are going to have to figure out how to manage the access to that resource. Okay. You have probably seen many ways of doing that in the OS course, and those who have not done it will see many ways of doing that in the OS course. But the concurrence is the number one concern when you are doing parallel programming. Okay. Figure out what depends on what is shared with what, and then decide when one or the other can happen. Okay. If they can happen in parallel or concurrently, then you allow them to happen. If they are not going to give you correct result, if they happen in any order, then you force that order. Okay. So, that is the number one concern while parallel programming, and then other concerns we will get to shortly. And so, this is an expansion of that list of concerns. To be a good parallel programmer, you are going to have to understand what the parallel architecture is, right. I said that we will assume a PRAM theoretical model where I have got a set of processors and a memory that is shared across them, and then I am going to give you an algorithm. Okay. In order for that algorithm to work well on a given machine, you are going to have to see how well it maps to that PRAM architecture, and when it is different from PRAM architecture, what are those differences and can those be hidden. Okay. So, you have to be mindful of where the memory access are going to be slow, where the data communication is going to take long, and take that into account on top of the PRAM model, which does not account for those things. And so, you are always going to have the target model and will design for the target model. That is why I also said that when you do the assignment, although your program will run fine, probably correctly on your laptop, but if there is a significant difference in the architecture of the laptop versus the machine on which you eventually want to run it, then even the algorithm might change, or even the design choices that you made on the laptop may be different from what you would have made if you were running it on a slightly different architecture. Okay. And again, I am not going to stop repeating this until the end of the course. Think concurrent. Okay. That is one common problem with people learning parallel programming or writing parallel programs, that they continue to think in terms of the sequential programming style. They say here is the thread, it does this, that, and the other thing, not realizing or ignoring that at the same time some other thread is doing things with your variable. Right. So, if you simply see a program, you say this variable gets updated here, here, and here. If that variable was shared by somebody else and you did not account for that, it is not going to get updated just here, here, and here. Okay. And so, you have to be extremely mindful all the time of that concurrence issue, and that is where the majority of the bugs come from. As a matter of fact, I always say that you have got to think of other threads always as adversaries rather than threads cooperating to solve the same problem, in the sense that if you are going to assume that that thread is going to play nice, it is definitely not going to play nice. Okay. Every race condition that you think is rare is going to come in your program, okay, when you run it or test it, or especially if you demonstrate it to somebody else. All right. So, those are the rules of the programming. So, think concurrent. At every time you are not only thinking in terms of what I am doing, but what I as one of many is doing. Okay. There are other n minus 1 things doing whatever they are doing. And then the other part is the synchronization. Okay. Once I have figured out that these are shared and these depend on these other things, then how they should communicate, how you should manage their access, how you should stop one from accessing the other, or how you should make other processes, threads, whatever that will do this for you, do the management of shared resource synchronization or communication of data, and so on and so forth.
So many of the challenges that you mentioned in this slide are basically probably challenges which were there with sequential programming long back.
It exists in the, so many of these will exist in the sequential programming, but in the concurrent domain.
Right. What I wanted to know is what is the state of the art in automating these?
Very poor, very poor. And that actually brings us to the last point here, which is you employ high level constructs as and when you can do so. Okay. There are some high level constructs which is about automating some of this, and OpenMP basically has a lot of these high level constructs which says that this stuff should happen in parallel, and I do not want to deal with how they talk to each other. And high level constructs not only help you make programming simpler, but also you know that that has been debugged, you can safely use it and not worry about those race conditions, at least in that part of the code. Okay. The problem is that not everything can be or at least as the state of the art is, not everything can be handled by high level constructs. Okay. And so, you would like to let the compiler deal with it. Right. I write a sequential program, I tell the compiler run it on this architecture which has so many processors, so much memory and the other stuff, and it compiles it. In some cases, especially in the research domains, some success has been demonstrated, but it is far from actually being applicable or useful in large applications in real contexts. So, there will be typically some mixture of high level constructs and user coded careful parallel code that will eventually make the system faster than just using parallel constructs everywhere. In fact, there are cases where you will not be able to use parallel constructs at all. Okay. So, as the slide says, there have been significant and milestone attempts for compilers to get some parallelism extracted, but typically the context of what the application is trying to do, what the architecture is, becomes so complex that it is hard for it to be managed in an automatic way. Okay. And so, invariably you are going to have to help the compiler even when you are using it, right. So, even when I said OpenMP has these high level constructs, by the fact that they are constructs tells you that you have to call them, right. It is not inferring from your sequential code how to make it parallel. You have to say this region is to be parallelized in this fashion. Okay. You are not doing it all the way, but you are still providing what runs in parallel, what is independent of each other, and here are these 10 things that can be done at the same time, but then this 11th thing has to happen only after all those 10 things have been done. So, compiler although would be ideally suited, or we would want compiler to be able to take care of the parallel programming problem for us, but it at this as the state of the art is, it cannot. And so, here we are, and which means that when you start to program, you use as much high constructs as possible, but at the level of the application, as the programmer of the application, you will be responsible for managing the parallelism. What are the things that run in parallel, what is the level of parallelism, what is the management of important resources. So, there are some resources that can, as you will see, some resources can be managed automatically, there are some resources that you are going to have to manage yourself. And of course, so those last two items basically say that you have got to think in parallel instead of starting to think if here is one program, one sequence of instructions, and you have got to understand how parallel access to data structures and parallel algorithms to do simple things like addition to somewhat less simple things like sorting to an even more complex thing can be done. Okay. So, let us stop at this point.